Okay, today we're going to review integration. This review will be shorter than what we did with derivatives. For one thing, our work with integration is much more recent, so you're more likely to remember. And the other is that we actually see less of the AP exam focused on integration. It's not 50-50, it's probably more like 70-30 or 65-35 in favor of the work with derivatives. So there's less to review with integration. But just to get started here, so remember that we have two different types of integration. The definite integral tells us about, it gives us a numerical value. It's a number. And it tells us about, that number tells us the signed area between a curve and the x-axis. So if we have the definite integral from a to b of, let's call it n of t dt, then it would tell us the signed area between n of t, the function that's behind the integration, and the x-axis. That number also tells us about the change in y values on the antiderivative of t. Of n of t, antiderivative of n of t. So normally, and what we need to be used to doing is thinking about whatever function is sitting here as the derivative of something. This is a derivative. Whether or not it's marked as such, it is a derivative. And the integration then is telling me, the definite integral tells me something about that function, the derivative function. It tells me about, graphically, about the area between that function and the x-axis, signed area. That also tells me, the definite integral also tells me something about the original or the underived function, the pre-derivative function, antiderivative. It tells me how much the y values changed there. The indefinite integral, which might look like this, tells us about f of t. So it tells us about an original function, not anything specific about that original function. It just describes that original function. Remember that if you're doing a definite integral, that you don't need the plus c, they cancel out. If you're doing an indefinite integral, whether you're in a differential equation setting or anywhere else, you always need the plus c. Looking at some more reminders, the fundamental theorem of calculus, you have to know this. This is a big deal, and it is the fundamental theorem of calculus together builds for us the relationship between derivatives and integrals and allows us to do a whole bunch of application problems. The first bit of it we've talked about a lot, that if I integrate a derivative, then I get change in y values on the original, so I get f of b minus f of a. Many times starting a definite integral problem is nothing more than writing that and then thinking about, okay, what can I do with it? We've also seen it in problem settings where we think about the integral of a rate of change as giving us not amount, but amount of change in the original. So in words, that's what's really going on. So we would look for words like rate, changing at, something like that to indicate to us that we are given a derivative function and are being asked to consider an integrated function or an amount function. We also know that derivatives and integrals are inverses. So if I take the derivative of an integral, they cancel out and I get what I started with back. And if I integrate a derivative, they cancel and I get what I started with back. Also remember this, we haven't seen this, and actually I don't think there's an example of this in here, but we did these, I think just before spring break, where we were asked to find the derivative of the integral from, say, 3 to x squared of sine x dx. Sorry, that's not right. Let's fix that. Let's make it sine t and dt. So we would always have two different variables there. And remember, the idea there is that the derivative and the integral cancel out, but then I'm evaluating that integrated function at x squared. So when I go back to find the derivative, I'm going to have chain rule. So this is going to be equal to sine of x squared dx squared, and the derivative of x squared is 2x. So in that case, the derivative and the integral do in effect cancel out, but you have to remember that because this endpoint is itself a function, then in my answer I end up with the derivative of that function. For this one, you can prove that to yourself. You can actually integrate sine. You know the rule for that. You can plug in 3 and x squared, and then you can go back and find the derivative and see that it is indeed that. But that's the little shortcut that we developed, that if we see a derivative and an integral, we know they cancel out, but then I have to consider if one of the endpoints is a function, then when I find the derivative of the integral, I get the sine, t becoming x squared, and then d meaning the derivative of x squared, or the 2x. Also remember, because sometimes we see this, that if we were to have dx of x squared to 3 of sine t dt, then because the 3 and the x squared are reversed, I would end up with negative sine x squared dx squared times 2x. Then we have a list of techniques for finding the definite integral. From a table of values, we're doing Riemann sums. I have an example later on here just to remind you of how you set up a left hand or right hand, a trapezoidal and a midpoint, and I'll get those started for you so you can see that. If I'm asked to evaluate a definite integral from a graph, I'm thinking area, 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 area. Typically, I'm either given, if it's something curved, I'll be told what the areas are. If I'm not, then it should be something straight line, so I can use area formulas, triangles, rectangles, that sort of thing. Remember that the integral is signed area, so if I'm asked to evaluate an integral, I have to be constantly asking myself, is my value positive or negative? And so don't forget to consider that. I think you know when it's positive or negative, but sometimes you forget to consider it. So consider that it can be negative. From a function rule, we have rules for finding antiderivatives, and we've been doing that now really since spring break. And then we know about Math 9 or FNINT if we have the calculator. So just a reminder of the antiderivative rules. For integrating a constant, we get kx plus c. We see this fairly often. So this is another situation where paying attention to your independent variable counts. Remember that this is, k typically represents a constant, 3, 5, 7, 9. And so that integral then, this says my variable is x, k is a constant, so I integrate back to kx plus c. Think about what if I were asked to integrate k dk. That would be a different answer because in that case k is a variable, then the dk tells me that. So that's when I would get the 1/2 k squared plus c. So make sure that you read carefully for what your variables are and that you're interpreting the problem correctly. The next question, I have x and dx, so I'm in terms of the right variable. It's a good old power function. I add 1 to the power, multiply by the reciprocal of the power, and then my plus c. 1 over x, we've seen a lot, natural log. Don't forget it's of the absolute value of x plus c. This is one that you often forget because of the k there in front of x, so make sure that you're thinking about this one. You don't want to miss the easy questions, and that's an easy question if you know the rules. So, for example, the integral of e to the 2x dx is 1 over 2 e to the 2x. Plus c, not k, but x. E to the 1/3 x would be 3 e to the 1/3 x plus c. So you do something with that coefficient if there is one. If it's just e to the x, then its integral is just e to the x. Here we are with sine and cosine. We have to go back and remember which of those is negative. So I know that cosine comes back to sine. Then I'm going to stop and check the derivative of sine is cosine. Everything's good. It matches. I know that sine comes back to cosine. The derivative of cosine is negative sine, so I need the negative there on my cosine. The derivative of secant squared is tangent. Remember that secant squared is the one that you never separate out when you're doing integration with substitution. You always leave secant squared as its own unit because it integrates directly back to tangent. Do a little substitution example, although we've seen these fairly recently, just to remind you of what that's all about. So I need substitution if I see a product that can't be simplified. Not able to simplify it, not simplified. Or I can't simplify it really. Or if I see a composition, any composition that I can't simplify. So if I see a product that I can't actually multiply together to get a sum or difference, or if I see a composition that I can't actually typically multiply like FOIL or something out to get sums added or subtracted, then I have to do substitution. You should never start to integrate something that involves a product or that involves a composition. You need to do something first, either substitution or actually perform the operation that's described. Do not start integrating if you're looking at a product or a composition. Do something else first. So in this case, I actually have both. I have a composition here in this term, e to the cosine 2x, and I have it times sine 2x. And actually sine 2x itself is the composition, but the more complicated composition is over here. So I'm going to start with that and hope it works out for me. So if I need if I'm going to try substitution, then u is going to be the inside piece of my composition, or my more complicated composition. So u is cosine 2x. Then I find the derivative of that. The derivative of cosine is negative sine 2x. And then don't forget, I need chain rule here to find this derivative, times 2. Then I'm going to solve for dx. So dx is du divided by negative sine 2x times 2. If I go to substitute in e, the cosine of 2x becomes u, sine 2x stays, dx gets replaced with du divided by, and I'm just going to go ahead and multiply those, negative 2, although you don't have to, sine 2x. Then I stop and cancel and hope the x's cancel. If the x's don't, then I have to go back to the drawing board and try something else. In this case they do, sine 2x and sine 2x. So now I have all u's and constants. I'm ready to integrate. I can pull this coefficient out, negative 1/2. Be careful that you don't pop the 2 up to the top just because it's hanging there by itself. It stays in the denominator. It becomes negative 1/2. Integrating e to the u du. I am paying no attention to what u is equal to. I am not even looking at over here at my substitution work at all. All I'm doing is integrating e to the u, which is easy. It's just e to the u plus c. Then I go back and pay attention to what u was. Don't try to, don't pay attention to u before you need to. The only thing you should ever need to do with u is substitute it back in. You aren't actually integrating u itself ever. Only what's been done to you. Only the e. Only the square on u. Only the 1 over u. So that's what you're paying attention to, not whatever u itself was. Remember the properties of the definite integral? We just talked about this one, that if my endpoints are reversed, I get the opposite of if they're going left to right. So this example would be, for example, if I had negative, if I were running my integral from 5 to 3, smaller to bigger, bigger to smaller, then that's going to be the opposite of 3 to 5. This one is the one that you miss algebraically, but not numerically ever. So this one, we now know how to integrate directly. So we could actually integrate that. So that's just a definite integral. C is a constant. There's my variable. X is my variable. So if I integrate C, it comes back to Cx. I'm evaluating from A to B. That gives me C times B minus C times A, which is C times B minus A. So I could actually do it algebraically, or I can just know this little rule. But don't just integrate C and get C. Remember that C is a coefficient, so when it comes, X is my variable there. So when I integrate, I'm going to have something that involves X as part of my integral. Number 3 tells us that we can break integrals up if we'd like and just go A to C plus C to B. Number 4 tells us, and we use this one a lot, that we can move coefficients out in front of integrations or leave them inside, whichever is more convenient for us. And number 5 tells us that if the y values on one function are bigger than the y values are on the other, then the integrals are bigger too, which makes sense because the integral, remember, is calculating area. So if the y values on G are bigger than those on F, then the area under G has to be bigger than the area under F. Okay, a little bit of reminder about calculating left, right, and midpoint Riemann sums. I noticed some of you were struggling a little bit the last time we saw one of these, so we're not going to do this full question. This is a velocity time, and so we're being asked to find out how long the stretch of road is. So we're being asked to find distance, essentially. I notice that all the velocities are positive, so I don't need to worry about absolute value, which I normally would with distance. If I were asked to do a left-hand sum with 10-second intervals, then the way my left-hand sum would start is always change in x times the y value. If I'm doing left-hand sum with 10-second intervals, then my change in x is 10 times left hand, I would use the y value on the left, so 0, plus, I'd do it again, 10 times 44, plus 10 times 15, and so I'm stopping at 10 times 35. If I were doing a right-hand sum, I would start with 10 times 44, plus 10 times 15, plus so on, and I'd stop with 10 times 44 out here on this end. If I were doing a trapezoidal sum, I would find the left and right-hand sum and average them. If I'm finding a midpoint sum, I can't do that with 10-second intervals. So let's say I wanted to do a midpoint with 20-second intervals. In that case, I do think it's helpful to draw the little bridges. In that case, I'm going to do 20, change in x. Midpoint is the y value in the middle, 44, plus 20 times y value in the middle, 35, and so on. And remember that this is giving me, velocity is, because we have a special word for it, it's not quite as generic as saying integrate a rate of change to get amount of change, but that's what's happening. Velocity is a rate of change of position, and if I integrate rate of change of position, then I get back the total amount of change of position. Remember that with these examples, we often see, remember the difference between this, that if I integrate a to b of velocity, I get change in position, or displacement, if you like to call it displacement. If I integrate a to b of the absolute value of b of t, I get distance traveled. So don't forget to read the question carefully to see which one you're being asked for, whether you're being asked for change of position, whether you're being asked for distance traveled. The example to kind of put your head around is, I walk my dogs every morning. So I get up, I walk my dogs. From time, 0 until time 16 minutes later, I walk them for about an hour. So from time 0 to time 16 minutes later, my change in position is 0. So if I just integrated 0 to 60 of my velocity, I would get 0 for my change in position, because I end up back at home. If I want to figure out how far I actually walk, then I would need to integrate 0 to 60 of the absolute value of velocity, because exactly half my velocity, I guess, is getting further away from my home, and half of it is getting closer to. So the overall integral is going to be 0, the integral of signed area. But I want to count going out and coming back as distance travel. That's part of my exercise. And so I need to do the absolute value of velocity. So just remember to pay close attention to those words. This is absolute value. If you don't see absolute value, then you're calculating change of position or displacement. You're calculating how far you get from the starter. Also remember in these types of application problems, there's often an initial value. If there's an initial value and you use a definite integral, then you do your initial value plus definite integral. If there's an initial value and you're doing an indefinite integral, then that initial value shows up to help you find C. But you use the initial value in either case. Okay, I think that's it for this video. And then the next one, we're going to talk a little bit about applications of integration, the area volume, and differential equation problems that we've done really recently. So that video is really short because we've just done those things.